Welcome to RISE Learning Machines seminars. I am Olof Mogren. I'm a machine learning researcher here at RISE. RISE is Sweden's public research institute, and this is our open weekly seminar on machine learning and AI. This particular seminar is organized in collaboration with Climate AI Nordics, a network of researchers in the Nordics, focusing on AI to fight climate change. This meeting will be recorded. Let us know if you want to be removed. And the fact that we record these seminars also means that we have a great collection of amazing talks on our YouTube channel. So go check that out. Today, it's my pleasure to introduce John Martinsson, who is a PhD student here at RISE and at Lund University. John is focusing on machine listening using machine learning, focusing on analysis of audio data with its applications to bioacoustics and biodiversity monitoring. And central interest of his is also to streamline the process of labeling bioacoustic data. And the topic today is efficient and precise annotation of local structures in data. With this said, I will hand over the word to you, John.
Thank you very much. Good. So welcome to this presentation on efficient and precise annotation of local structures in data. My name is John Martinsson, and I will be going through a lot of the presentation that I did recently when I took out my licentiate thesis, sort of an overview of what I've been working on so far during my PhD. So the motivation for my work using machine learning for audio analysis and especially labeling is consider these sounds of the world. This is a map of an initiative that's called Apori, where people just go out and record small snippets of sound of different natural environments. We will zoom in on a particular environment just outside of Gothenburg. We can see that we are in a small forest patch, somewhere close to an urban area. And we will listen to this recording. So this audio recording is telling us an entirely different story about this little forest patch than what we can see from above in this image. So these types of data are very much complementary, and they sort of tell you different things about this environment. So we need both of them to fully understand and measure our natural environments. And this is a spectral representation of this audio recording. So you can see some high frequency sounds here, and these are different types of birds that are sort of singing here. And this is at the core of my PhD thesis, trying to, how can we automate the detection of these different types of species and count them, their vocalizations, classify them, and so on. And if we can do this, we could sort of use all of this data that is available through these types of initiatives to start building maps over the world of bird richness, mammal richness, amphibians, all animals that are sort of vocalizing and making sounds. We could start measuring them in this way, which will be sort of necessary. Biodiversity loss and ecosystem collapse ranks third on a 10-year global risk assessment. So this will cost us a lot to lose all of these birds, animal species. So there's a huge economic incentive to monitor this and make sure that we are maintaining these populations. And recently, 190 countries committed to actually protecting 30% of biodiverse areas by 2030. In Sweden, I think this, at least for terrestrial sound, part means that we need to double our protected areas. We are around 15% right now. We need to double that to 30. And we also need to ensure that, well, these areas are actually biodiverse. How do we do that? And how do we automate that? And how do we sort of objectively quantify that, well, we have protected this area and it's actually a valuable area to protect. So this is where I want to make my small contribution by sound analysis and complement other different types of data. And we can start seeing these kind of initiatives come up all over the world, like global biodiversity observation systems unite, monitor, and guide actions, they envision some sort of national biodiversity observation networks, and then they collaborate on global scales. We have this typical picture with satellites, drones, images, eDNA, cameras, and I'm sort of advocating that we need to listen to nature in addition to look at it to fully understand what is going on. So a lot of the time, this sort of audio part is missing from these pictures. And just on personal experience before we go into the actual methods, what do we need? Well, for example, projects is I've been working on lemur localization detection from Madagascar rainforest from these type of passive acoustic monitoring devices where we have months or years of data. Bird dawn chorus detection with SLU, capercaillie vocalizations for wind farms. We want to understand how the wind farms affect capercaillie populations. And just recently, guillemots at the Stora Karlsö. But sort of all of these projects have the challenge that, well, initially we have like months or years of audio data, but we have very few annotations, so it's very hard to get started. And I sort of started to go into my research in this direction because of this need that we need to sort of get the ball rolling and keep it rolling. So we need some efficient and reliable ways to annotate these sound events. And they are needed because, in particular, labeled validation datasets, I would argue, are needed to measure progress. Without good quality validation data, we cannot distinguish a bad model from a good one. And also, for actually deriving the models, labeled training datasets is a very sure way to get better and better models. You can sort of model away parts of this by unsupervised or semi-supervised learning, but there's no way to get around it. We need to specify our model to find it. So we need good labeled validation datasets to measure progress. And so this brings me to annotation. I'll provide this little example here with 3 different sound events. We have this sort of chick, chick, chick bird going very high, and then we have more melodic bird going down below here in this spectrogram. And then we actually have some other bird which is a bit hard to hear in the middle of this frequency band. And strong labeling of this data would mean that we actually give a segment label, so go through this like these bounding boxes or mark the onset and offset of these events in time, and then give a class label to each of these segments. What I've been looking mostly at is weak labeling, where the annotator is asked only to provide a class label. So the annotator is given segments of the data and gives the class label to that segment. So imagine if this audio was pre-segmented into these small chunks, and the annotator just goes through and clicks, well, here is absent, present, so on. Which is a task that is both easier to understand for someone who has not done it before, and it's also easier to perform. I tried just annotating strongly, like a couple of 30 minutes of this, and that my arm started hurting, but clicking is sort of, that's sort of fine. That is why I'm looking into these types of methods. So just a short algorithm on this type of annotation of data. Well, we start with some unlabeled dataset, DU, with a bunch of audio recordings in this case, n of them, and some model that we want to train, and some performance criterion that we want to achieve, tau. And we want to label data out and also a model. We start without any labels at all, and we start with some valuation performance of this initial model, probably poor without labels initially. And then while the model performance is less than what we want it to be, we sample and remove one of the recordings from the unlabeled data. Some annotator gives a label Y to this audio data X and adds that to the labeled data set. We update the model using the labeled data and reevaluate, and continue doing this until we achieve satisfactory model performance. Then we can stop. And Sure, you can see. Need to move that. One of our recent papers, we have been looking into sort of a weak labeling theory, basically putting this weak labeling procedure into some sort of theoretical framework, currently under review at TMLR. We looked at, in particular, two different weak labeling methods. One, which is the oracle method. And this is an upper bound. We cannot know this in practice, but it's good to know what you can achieve. So basically what this does, it uses the ground truth onset and offset of your events, constructs the segments, and then you ask the annotator to provide presence or absence labels for these query segments. So basically this will derive the ground truth labels using a weak labeling approach. And then we do the major chunk of analysis on this fixed method, which is sort of commonly used in practice, where you divide things into equal length segments, and then you ask someone to give a weak label to that, just presence, absence for each of them, and you get these a bit coarser annotations in there. Sorry, I missed mine. So the X's here is a whole recording, right, from this unlabeled data. That's an X. The oracle method provides the label y_org, and it is whole labeling for this recording and then fixed label. So I'll talk more about that soon. And then another method, which is machine-guided labeling of audio, where the goal is to sort of go from this, perform better than this fixed method and try to model the oracle method a bit more. So can we, in an automated way, approach this oracle weak labeling process and model that using the labels that we get during the time we're labeling? We call this adaptive change point detection. So we use change point detection to split these segments, and then with each new label, we update that algorithm to hopefully perform better. And another recent paper that I just thought I would mention that just got accepted to USIPCO from two of our really great master thesis students that looked at aggregation strategies for efficient annotation of bioacoustic sound events using active learning. I should note that these arrows here indicate which part of the algorithm that they are sort of focusing on. So these parts are focusing on line 7 here. So given an X, how do we improve the Y? And this is focusing on line 6. How can we sample the X from the unlabeled data in an intelligent way? I sort of like to call this part focusing on line 7 here active labeling, because we're basically biasing the labeling process using the model. When typically in active learning, we would do some active biasing the sampling process, changing how do we sample these X's, the audio recordings, based on the model to be more informative. And the rest of this presentation will be about more of this active labeling part. So let's jump into the weak labeling theory. What we look at here are two methods. I basically introduced this so we can go quickly. The oracle method, which derives the ground truth segments using the actual onset and offset of the events, and then ask for weak labels of these, and we get a nice labeling of this. And then the fixed length, dividing it into equal lengths. And of course, if you use this fixed method and increase the number of segments, you can get a bit better accuracy, but at a higher cost. You need to handle more segments, you need to click more and verify absences in more of them, and so on. And you can go also a bit too high, depending on how you model your annotator. I will explain this later, but you can lose recall if you have too short segments, so that it's not covering enough of the event that you can sort of detect that event in that. We will do query length by DQ. This is length of the queries, and the goal is to compute the expected label quality of this fixed weak labeling process and number of query segments needed. And to do this, we need to assume an audio distribution and an annotator model. So let's zoom in on this. The audio distribution that we assume here, or basically actually it does not need to be an audio distribution, it's basically an event distribution. So it's a single event occurring with length d. It can occur anywhere with equal probability in this time series, or in this audio recording in this case. And then the annotated model would indicate presence in Q2 here. If it occurs here in Q3, it overlaps with both, so we get presence in Q0 and 1, and so on. And here the annotator models indicates presence in Q5, but misses presence in Q6, even if there's a bit of an overlap. Which brings us to the actual model of the annotator that we assume. We assume that it is feasible for an annotator to detect this event in this query if it's sufficiently covered. So if the intersection between the event length and the query length divided by the event length is larger than or equal to some gamma. So basically, if gamma is 0.5, we need half of this event to be in this query for a presence label to occur. And we call this gamma the annotator criteria. So just quickly, the average label, query label accuracy in the cases of overlaps would be computed like this. So we look at each of these queries by themselves, and we compute the average of this. In this case, where we missed it, we have quite high accuracy because most of it is absence label here, and it's Garmin absence label, and then we have quite bad accuracy, I would say, in these ones because the segments are too long for these event lengths, not adapted for it. So even if we get these present labels, most of it is actually absence. And on average, the accuracy would be, for this case, like 0.35, 0.47. And to do this in expectation, we need to consider all of these overlap cases and derive this sort of area under this query label accuracy curve when we consider all cases. You can see down here some event occurring with equal probability relative to this query and the sort of corresponding query label accuracy that you get out of it. And in this example, gamma is 0.5. So you see that when half of this event is inside of the query, that's when it triggers, because then it's sufficient amount of the event is in that query segment for the annotator to reliably detect presence, or that's how we model it. So basically, we want to find the area under that curve and then normalize it. Which brings us to the main theorem of this paper. I'm not going to go through all of the details of this, but you can actually get a closed form solution for this and get the expectation for the label accuracy in case of overlap between a query segment Q of length dq and a single event E of deterministic length dE. And it's this expression here, when the presence criteria for the annotator is gamma. This case down here is when annotator presence criteria can never be fulfilled because the query segment is so short that it can never cover sufficient amounts of the event. And using this, you can start to derive, for example, the optimal query length for this method, which depends on gamma and also on the event length you're looking for. But changing the event length just scales this. So we look at the event length 1 here. And what you can see is, well, if gamma is approaching 0, then the optimal query length will be approaching 0. Because if the annotator can detect arbitrarily small fractions of an event, then the best thing to do to get the optimal or maximum label accuracy is to just split it into arbitrarily small segments and have the annotator label that. But of course, that comes at a huge cost. So that's something that we will look at later. And the corresponding maximum expected label accuracy, if you use this optimal query length as a function of this gamma criterion, looks like this. So you can see if you can detect arbitrarily small things and you pay an infinite cost to label very small segments, you can actually get label accuracy 1. But if you have some more realistic assumptions about the annotator anywhere between 0 and 1, One being that the whole event would need to be inside of the query segment. Then this is sort of the expected label accuracy that you can get out of this process. And some additional results. You have to sort of go into the paper to see this. But what if we have different event lengths? Of course, this is a very simplistic assumption that we have a deterministic event length and a single event in a recording. If we have different lengths on sort of distribution, normal and tested gamma and some realistic ones, it doesn't change too much. It still follows the theory. And also you can actually use the expression we derived for the expected and just do numerical integration over the distribution if you know that distribution you want to, or have a reasonable assumption about the distribution of event lengths that you want to annotate. And what if we have multiple events? Well, yeah, then it starts to sort of, so the theory for this one single event is this black line. Then it starts to diverge a little bit, but it's still sort of, I mean, breaking this assumption is not too bad. Of course, if it becomes extremely dense, which is something that we're assuming that's not occurring, then it can start to become troublesome. So the theory holds for more sparse-ish recordings, I would say, for sparse-ish events. And then an additional annotation cost fixed relative to this org. And you can see that this fixed labeling method is, I cut this here, but if you actually have this annotator criterion approaching zero, then it's infinitely more costly to do the fixed method than the Oracle method. So this is why we want to model the Oracle method, which brings us into the next session, machine-guided labeling. Maybe I should pause here and see if there's any questions for the first part. If I went too quickly or if it's clear.
That's a good idea. Do we have questions? I think I have a couple of questions. You said the theory holds for sparse events. What about varying recordings where you have, it could be sparse, it could be dense at some times, and it could be sort of varying lengths of your events as well?
Yeah, so varying event length is not a problem. It's what we're looking at up here. And here we assume normal distributions for event length, but this is still for a single one. I mean, if you have, it's hard to, I mean, if it's in expectation is sparse what you're looking at, then it should sort of hold. But if it's always dense, then it starts to not hold. So it's hard to answer your question if it's sometimes, I mean, it will not be true for the recordings that are dense. That's basically what I.
But then again, sort of started with assumptions from your observations on real data.
Yes.
May I ask you one thing?
Mm-hmm.
Just curiosity. Sorry, Andrea from Rice also. PhD student also doing working with sound also. But so just curiosity, what would happen? What do you think would happen if you would have same sort of events occurring at the same time? So let's say the same bird, two birds of the same species singing, overlapping basically to each other by some degree.
Yeah, so that's something that we are assuming is not occurring for this theory. So it will not hold for polyphony, or at least we need to develop it further. This is but that's not assumed in this model.
Okay.
So it won't predict that.
Okay, thanks.
Yeah. So that's a good question. Polyphony, and I mean it's very closely related to density. That's something that we have assumed away for this initial analysis. I think I need to continue, otherwise I will go over time. So machine-guided labeling. Now we have a bunch of data, like in all of these projects, and we want to analyze it. So we need to get started. And in this part, we have this annotator, and we want to perform machine-guided annotation and then update the machine learning model with each new annotation and sort of hope to achieve some sort of self-improving loop here. So for this audio, you might have these target events like this in a recording and then try to automate this segmentation using change point detection or some other method that actually tries to use the structure in the data to detect the change points and then construct these query segments from that. And then the annotator gives presence absence labels using these, and we update the model. And over time, the goal would be to sort of approach this Oracle weak labeling. This is basically what we try to model in this process and doing that adaptively during the annotation process. Of course, we might never achieve exactly this, but could get closer at least. And the actual method, the adaptive change point detection method proposed in this paper works like this. So the annotator is given an audio recording and a model, HK, that is used to guide the annotator. And K here indicates the number of labels that we have. So at 0, we have no labels. But we can still detect or predict presence of the target events for this audio center at T. Even if they might be semantically wrong, it can still sort of react to the structure in this data. I will explain this model a bit more later. But so you can see we get this initial very noisy thing, and it actually goes down where the target events are. So the semantics are flipped here, but that's because we have no labels to anchor the semantics in. But it still detects or reacts to the structure, which is sufficient. So then we compute magnitudes of changes in this pseudo-probability curve. And we try to detect the B-1 most prominent peaks, if B is our budget, number of query segments. And then we split along these peaks, along these x's in this case. And the annotator, or the modeled annotator in these simulations, indicates presence based on if the event is inside of this query or not. And then we use the label to update model. I should note that we are looking at a held out test data point here. So we're actually running this process on some training data, not on this exact point. But this is informative to sort of see what happens or changes. So after one update, we can see that, well, now this pseudo probability curve is actually anchored in the semantics. So we get something which is positive or closer to 1 for the actual target events and then closer to 0 for absence. We get much cleaner already after one update in this case. And we can compute the magnitude changes, get some new segments and a slightly better label, I would say. If you compare, this is a bit tighter around these two events. And then we continue 19 more times. And now finally, after 19, we can see that we're actually able to resolve these two events. So we're approaching something that gives better and better labels using this same weak labeling method and the same number of segments. So this is the sort of main idea. It's sort of simple idea, but it seems to work, at least for the recordings that we're looking at. And also using these sort of assumptions, it will be more troublesome if there's a lot of things going on at the same time and if there's polyphony and very dense. So this is sort of still following this, starting, I mean, with a more easier thing and then hopefully go into the harder things later. But it can still be useful for these kind of data because they do occur. And the underlying model that we use looks like this. So we assume access to some foundational model or some embedding model that actually does some reasonable structuring of your data. In this case, we use BirdNet for these bioacoustic data. I should note that what we're looking at are never birds, it's other animal species. So classes are at least disjoint, but we have some huge foundational model that has been trained to sort of learn some sort of structure of the audio space. And then just to illustrate, we might get in this embedding space, just imagining 2 dimensions, positive events might sort of cluster somewhere, and the absence events might cluster somewhere else. This red one, illustrated by the red triangles here. We have used a prototypical network. It's this HK function that I showed before with the zero probability curve, the orange one. And we just randomly initialize these prototypes in this space from the beginning. And we don't have any labels. So we put them somewhere. So the negative prototype could end up to the natural cluster of positive or presence classes. And then just go through segment-wise this whole audio recording, you embed it. This is just illustrating how it's sort of meant to work. And in segment 4 here, we have these positives, maybe the embedding ends up here. And then we use the zero probability, it's computed just, this is softmax normalization of the distances to the closest prototype, so negative and positive. And if it's close to the negative, it will be zero probability closer to 0 and closer to the positive and closer to 1. So this is sort of also an explanation of why the sort of curve is flipped initially, because these are randomly initialized. So if this happens, then this can happen. We actually get zero probability predictions close to 0 for the sort of presence class, because the negative prototype ended up closer to it than the positive. But it does not matter if this curve is flipped, because we're only interested in distinct changes to detect the change points. And then as you update with more and more labels, these prototypes, which are just running averages, should start to move towards their natural clusters, given that you have not too much noise in your labeling process or too bad initial state of this model. We did not see that happening, but I guess it could happen. So that's a drawback. And just a qualitative example, comparing these two, just adaptive change point detection labels and fixed labels. When we use this and we have sort of converged and started to go towards something that more closely resembles this oracle method, then we can know that there are at least 3 events from these labels, while fix in this case would give us the information that, well, there's at least 1 event here, because we have no absence segments between the presences. So, and this is especially important for evaluation. So I'm sort of stressing this, that for evaluation labels or creating a data set to evaluate your model, then these kind of labels can be very important, especially if you're interested in counting occurrences, which is something that we're often interested in bioacoustics, sort of counting how many animal vocalizations are there, and can we sort of get some estimate of the frequency for each animal, and maybe start to disentangle how many animals were there and so on. So then these counts are very important. And some quantitative results. We're evaluating this on 3 different presence-absence datasets that we have generated using real audio, I should say, at an SNR of 0 with meerkats or dogs or babies. And annotated criterion for all cases are 0.5. So half of the event needs to be inside of the segment. Annotator returns the wrong label with probability beta. So here the annotator is always returning the correct label. Here the annotator is returning the incorrect label 20% of the time, flipping it. And since we have mixed this data together, we know that there are exactly 3 events occurring in each sample. So this means that we can know that it's solvable, this task, using only or exactly 7 segments. That's what you need to resolve this task for 3 events in an optimal way. So this is where the oracle method is defined, in the gray area here. I actually excluded the oracle from this plot because it is always one without any label noise. But we can compare the adaptive change point detection with how it sort of places compared to the oracle and fix, and also something we call fixed change point detection. Basically, the same thing, but it does not adapt or update the model during the labeling process. You can see that it sort of improves, at least in these low budget regimes. I think it's most, I mean, where you actually want to really press it towards where you can achieve. You can optimally solve this task with 7, and here is where it sort of performs the best. And then if you're allowing yourself a very large budget, then it does not necessarily improve things very much. Or I haven't looked too much into that, but that's what would sort of be my guess.
Question.
Yes.
How come the oracle isn't better than 0.3, or what does 0.3 mean here? It sounds like an oracle should be somewhere around 80% if you get the wrong label at 20% of the times.
This is an F score, so this is not, if it were accuracy, I agree, and I guess it would be like that, but this is very unbalanced data, right? You have very little presence classes and a lot of absence, so we have a huge class imbalance, and it turns out like this, the F score.
Yeah.
Because of that. So that's the reason. If it were balanced, I think you're right, it would be 0.8. Also for the F score. I'm not entirely sure, but that is the explanation.
Good.
It's
Thanks.
because of the class balance. Okay, so that is it. So in summary, we talked about annotation of data and this annotation loop. Some weak labeling theory to sort of put weak labeling into a theoretical framework. So we have some knowledge about this fixed weak labeling process and the oracle, and sort of where can we exist and how far can we push this, basically. So getting some framework for this. A method to try to model this oracle weak labeling process. And I did not talk about this work, which is more about machine-guided sampling of all. But this is also very interesting, and I think the combination of these two in the end will be what gives us the most. And it also, I tried to combine both, and it sort of shows some attention that is not that often studied in active learning. I think that a lot of the time you assume that the labels are sort of label noise is independent of the sample. And here you have basically a simulation of an annotator that definitely gives label noise that depends on the sample. If the sample is hard and the model sort of gives a bad estimate for the segments, then the labels will be poor. So if you always choose the hard sample, which is typically what you do in the hard sample for the model in active learning, then this model will fail more often. So it's sort of simulating this tension that is not always addressed in active learning, which I think is quite interesting. So maybe the hardest sample are not the best way to go if you actually account for that hard samples will be harder for the annotator to model. They're either more costly or give worse labels. That makes sense. So my supervisors are Olaf, who is hosting this seminar series, and also Maria at Lund University. I'm a PhD student in machine listening by acoustics. Thank you for listening. Now, questions.
Thank you, John. I'll start with a question, and the rest of you can think of your question meanwhile. So with the ACPD, it seems like the process is you start out with a sort of a model that's not really that perfect. So you get a lot of noise in your suggestions in the beginning. And it looked like you needed to do a few iterations until it started getting better. what is how many times do I need to annotate things for it to become good? Or is there an analysis on sort of the actual savings that you may get for the annotator?
I mean, when does it start to sort of outperform fixed week labeling, for example, in label accuracy?
Yes.
How many times do you need to annotate before that?
Yeah.
I mean, in this example, I think once. I mean, here we are outperforming fixed. So after one update, after the first update. But this is entirely depends on the underlying embedding function. I mean, how well that structures the space. It is sort of it is relying on a foundational model that has been pre-trained on something, and you will just want to use this to sort of specify a new specialized task. And if that does not structure your space for that task well, then I'm not sure, I haven't looked at it, but that's something that would probably be trickier, and then maybe you need more. But from this data that I've looked at, it goes surprisingly fast to get something that outperforms fix and gives decent labels. I mean, these are already at 1 or 2 seconds. Very typical sort of order of magnitude in the sound, at least, is to split things into 3 or 5 second segments, or even 10. And they're always compared with the same budget. Maybe I have a figure for this. Let's see. I know that I did this at some point. Can you still annotate? No. Maybe I can write. I remember at least. Now you need to trust my memory. But if you have sort of accuracy, label accuracy and expectation here, and you have, what do you call it, K, number of annotations, the fixed method, sort of, let's say that this starts around here, and then we have the oracle method, which is always 1, and they are constant. I do believe that it looked something like this. So it might have started a bit under this, or maybe even over, I'm not sure. And then it's sort of, yeah. I need to find that picture to actually, but this is how I remember the picture when I did it. And it definitely does not start far off to the fixed quality initially.
Cool.
That was a lengthy answer to that question.
Do we have questions from the rest of
Yes, I have a question regarding this positive and negative anchor business. Did you test any other methods for getting this binary HK, or not binary, but one-dimensional HK signal? I mean, you could do PCA, or you could use a classifier somehow. Or...
You mean how I choose to model this function HK here?
Exactly. So based on your model, you need some way to make it a one-dimensional signal.
Yeah, so I've only tried prototypical network, but you could basically model this any way you like in this framework. If you think something is better, then model it like that. And that's sort of nice. I mean, if you have data, maybe you don't even want, I mean, this prototypical network is based on neural networks, and you're using embeddings and updating prototypes. You could use very simple change point detection methods as well, just as long as they are updatable with the new labels. Of course, you could use something fixed in this framework as well, but then you're not using that adaptive thing. And you would just have the same label quality and expectation always. Did that answer your question? I did not try any other methods than prototypical networks for modeling this HK, but that's definitely interesting.
And in your experiments, John, the representation model has been fixed.
Yes.
But you update the prototypes.
Yes. So this model, the embedding function, this theta parameters, typically some neural network that is pre-trained. We never update theta. So we have constant embedding space. This is just a structure, and then we update the actual prototypes in this space. So the average of the currently labeled data. And initially, when we have no labels, then they're just random. Yeah. And of course, this is a illustration that sort of I made it so that it's clear how you might have multiple of these red clusters. And this is also something that is interesting both for prototypical networks, but also here I think it's sort of maybe you need multiple negative prototypes if you have that case and things like that. But this goes into the previous question, just improving this model HK. That could be one way. And also extending it to multiple classes shouldn't be too hard. I mean, you just need the number of prototypes that you have classes. I think maybe some other changes. Yeah.
Yep, thanks.
Do you have any suggestions for how to model HK? I mean, you mentioned PCA. So you mean
that
apply
would
sort of-
just before you have any labels, you could just do one-dimensional PCA, and that would give you a direction.
Yeah.
Once you have labels, it would seem natural to me to just fine-tune a network, and then use the classification output of the network as a HK. I'm not sure if you think that would be too simplistic for some reason.
No, I don't know. I haven't tried it, but I guess one thing that you could be worried about is if it sort of overfits and you start missing things, and instead of having this sort of general structure model. When you have very few labels, at least, prototypical networks are sort of nice. But I agree, and something that I thought about doing this work would be sort of including some model selection as well. I mean, at some point, prototypical, as you say, when you have more labels, this is a very limiting model, and maybe you want to retrain a larger thing. And then at what point should we select a new model to sort of retrain and inform these decisions? So basically including model selection into this. So you're not only adapting the model to the data, you're actually choosing new models depending on how well your labels represented in that. But that sounds very tricky, but it could be very interesting to look into. Any more questions? And we had some interest initially from the video perspective. I only talked about audio here, but I mean, at least the theory part is applicable to any time series. So I'm not sure how typical it is to split video into equal length segments and then look at each of these and indicate if something has happened or not. That might be different for different modalities. But also this adaptive method, I mean, if you have some embedding function that embeds a sequence or maybe one image at a time for a video, this is sort of the same thing. Then you might split it into adapted videos and look at each of them individually. It's harder with video to sort of get this timeline that you can look at once. But that could be an interesting thing to, I mean, how to display a whole sequence of videos at once. I have not an answer for that. In principle, I mean, if you just change the underlying embedding functions and things to sort of the general framework, I think here should also work for any time series for this adaptive change point detection method.
Yeah, absolutely.
Just
I have another question that ties in a bit to that. What about data that is not time series? What about data that's varying not in one dimension but in two? So images.
So you could apply it one dimension at a time independently, I guess. But yeah, You mean for the theory part, that is something that I've been thinking about. How to sort of, if you can extend this to weak labeling of segments in 2 dimensions and 3 dimensions. I think a good start is actually just to do that. Consider each dimension independent of each other and to get some sort of rough estimate. But then if you count the sort of covariance, I'm not sure. That sounds a bit more tricky. And for this machine-guided labeling, I would probably propose the same thing. Do it sort of independently, and it seems tricky to do both, but I have no answer. Maybe that's possible. Do you have any suggestion on how to do it?
Well, perhaps you can look at sort of gradients in some sort of a pixel space. But I don't know. Perhaps some general segmentation model or something. Segment anything. Could try to start giving you some boundaries.
Yeah. I mean like that. Okay, so if you have, yeah, that is true. So you could basically put in segment anything into this framework and iterate to sort of make it segment just the thing that you're looking for. That is something that we have discussed.
Yeah.
And depending on how segment anything works, if it sort of handles dimensions independently or not, I haven't looked at it. But then that could be a way to do that, yes.
Cool.
Cool.
Are we happy with the questions?
I'm happy.
I'm happy too. Thank you,
Thanks a
John.
lot.
And
Super.
Thanks.
we'll meet again June 12th. So we have a couple of weeks of break now, but June 12th, and we'll shortly announce the speaker for that session. Thank you.
You.